I'm glad you guys could all come out today for the colloquium. Our speaker today is Julianne Rainbolt of St. Louis University, and she'll tell us about determining when Bruhat cells contain only regular elements. We're glad to have her here.
Thank you for having me. It's great to be here. So you can see over here on the left, this is an outline of what I'm going to talk about today. So we're going to go through the outline a little bit, kind of like commercial here at the beginning, what you're about to see. So first I'll just do some, as probably most math talks start, I'm going to just do some background notes, define some notation, and quickly do some background that's necessary to even explain, begin to explain what I would like to talk about. And then I'm going to state a theorem by Steinberg. It's from 1974. He proved a theorem that raised questions to me. I wanted to know what can I do with this theorem? Can I prove the converse? Can I change the what ways can I change the assumptions? And it has to do with the title. It has to do with Bruhat cells, and he showed in certain situations these Bruhat cells contain only regular elements, and I'll define what these things are. I wondered if I could change this hypothesis or prove the converse of this theorem. So I'll then put some motivation there. And then we'll look at an example just in GL4 to try to guess what we could change with the theorem. Maybe is the converse true? Let's check it. Let's change one of the hypotheses and check it. See if there's something we can do to change the theorem a little bit. And then I will answer the questions that I posed for the case where our algebraic group is GLN or SLN. And so I'll prove a partial converse of Steinberg's theorem in those two cases. And then what I'll go into is, well, why do we even care about when Bruhat cells contain regular elements? Is it just a puzzle to work, or is there some importance to that? What can I use? If I actually figure these results out that I'm explaining up here, what can I use those results for? So I'll explain an application to those results, which is actually backwards from the way that I work. This application was actually what I was trying to do. And I realized, I saw Steinberg's theorem, and I realized if I answered these other questions that this theorem made me think about, I would be able to do this application, which is where I started from. The application is what I'm really interested in. So I will explain the application in general, and then I'll actually apply that application in a specific case. So that's the major outline of where I'm going. So now let's define some of these words I've been using. Right, so G tilde will be denote a connected reductive algebraic group defined over FQ bar. I know I have a wide range of audience here, and every time I talk about a connected reductive algebraic group, if you don't know what that is, I know probably a lot of you do. You don't, though, just think of the n by n matrices. So think of GL and FQ bar. So that is the n by n invertible n by n matrices with entries in the algebraic closure of the field FQ. Q is the power of the prime. Okay, so you can think of that as that's the sort of standard example to think about, but more generally, G tilde can be any connected reductive algebraic group. All right, what does it mean for an element to be regular? It's regular if its centralizer in the algebraic group has minimal dimension among the dimensions of all the centralizers. And if the centralizer is minimal, that means the size of the conjugacy class is maximal. So you can think of it either way. So now, if you want to think about it in this context instead of just a general connective reductive algebraic group, in GLN or an SLN, which of course is GLN with the elements of determinant 1. Regular means an element's regular if and only if its minimal polynomial is equal to its characteristic polynomial. So like if we're in GL4 SQ and look at unipotent elements, I'm going to write down all the conjugacy classes of the unipotent elements. If I don't put anything there, it's 0. And then I let it out. diagonal here. Let's be sure that this is clear, so I'm going to write a little meter. So there's ones on the diagonal and ones on the super diagonal there. I left out any? These are, I'm supposed to be trying to write down the unipotent conjugacy classes. I think I've got them all. It'll be 1, 1, 1, 3, 1, 2, 1, 1, and 2, 2. Yeah, that's it. I think that's all. Those are the unipotent conjugacy classes for GL4. All right? They all have the same characteristic polynomial. X minus 1 to the fifth. The characteristic polynomial is x minus 1 to the fifth. But this one is the only one that has also minimal polynomial, x minus 1 to the fifth. So this conjugacy class is the conjugacy class of regular unipotent elements. These are not regular. Anything conjugate to these are not regular. Unipotent. The conjugate to this are not regular. This is regular. Okay? So that's the example to think of. To give us some context here. All right. I'm getting used to the clicker thing here. Okay. All right, more background here. Let B tilde be a Borel subgroup in our algebraic group. If you're thinking of our GL situation, this is the upper triangular matrix. Upper triangular matrices, any upper with non-zero elements on the diagonal to make it invert. Yeah, that's the Borel subgroup. We can think. And T naught tilde will denote a maximal torus. B tilde, you can think of that as the diagonal matrices in GL. N tilde, the normalizer of our torus in the whole algebraic group. And that is a Bn pair that forms a Weil group. So W, by definition, I'm taking W to be this quotient group, which is N tilde mod T tilde. And for those of you who know this area a little bit, this is a Bn pair, and so we get a Weil group. Okay. All right. W with a dot on it will be a pre-image of an element in the Weil group in the normalizer. Right, because we have our N tilde in W, and it's N, and it maps to this coset, and T, right, because this is the quotient group. So if you take an element in here, which I'm calling little w, W dot would be an element here. All right, so that's enough of the notation and definitions. Let's get into the motivation here. Well, these connected reductive groups can be written in terms of these are the Bruhat cells now. So by the Bruhat decomposition, the algebraic group is equal to the union of B tilde W dot B tilde as we union over every element in the Weil group. Can break down our algebraic group in that fashion, and that's called the Bruhat decomposition. All right, and these double cosets here are called the Bruhat cells. So here comes now, this is leading up to now the title of my talk. Hopefully makes a little more sense what I was getting at. We have a Bruhat cell here. What I want to know, when do these Bruhat cells contain only regular elements?
So the picture that I should have of this decomposition, if I'm trying to think of something geometric, should I think of these partitioning G maybe in a similar way to how conjugacy classes partition G?
Unfortunately not, because you can be, the Bruhat, two elements, you can take two distinct Bruhat cells, and there can be elements that are conjugate to each other. And, if there's A, one Bruhat cell, and a B in another Bruhat cell, they could be conjugate or they could not be conjugate.
These are still disjoint, right?
Yes.
Okay. And does the
no.
component... Oh.
Well, yeah. Okay.
Yeah.
Yeah.
And the one with the identity,
Think about it a second, but yes.
The one with the identity, is it something special?
Well, if you take the identity, then it'll be the Borel subgroup, right? B,
Okay.
B. Okay. But yeah, what makes this so hard, though, is actually your question was I'm glad you asked it, because what makes this question, one of the reasons this question is interesting, is that these Bruhat cells are not unions of conjugacy clauses. Okay, so S will be the distinguished set of generators of our vial group. I'm not going to define what a distinguished set of generators means. That has a very technical meaning, but it has to, something you may already know. It has to be there's a way of attaching generators of the vial group with the root subgroups of your group, and that gives you these distinguished set of generators.
So are these simple reflections? Do they correspond to the simple roots? Or?
Yes, they correspond to the simple roots, exactly. It's the ones that correspond to the simple roots that they're coming from. All right, and a Coxeter element by definition, so I guess I'm still doing a little background while I'm doing the motivation at the same time. A Coxeter element is, by definition, you take these generators and you just multiply them all together in order. That's a Coxeter element. And also any conjugate of that will be, it's also called a Coxeter element. Why is that interesting? Why am I defining that? Well, because I've got this theorem now, Steinberg, that I mentioned in my introduction to the talk. Steinberg proved in 1974 that if you take if your algebraic group is simply connected, and your vial group element is a Coxeter element, a minimal length, then you do get this nice situation where the Bruhat cell contains only regular elements. Now you're using a word here I haven't defined, minimal length. Minimal length is, we had this distinguished, we have these generators. Just putting this up here to point to on the previous slide, I think, or sometime soon, not a slide or two ago. We have these generators generate W, and the length of a vial group element, well, you can write every vial group element in terms of its generators. That's what generators mean. And the length is the minimum number of elements you need to get these out elements. Right? Clear? So, if it's Coxeter and minimal length, then this cell contains only regular elements. Now, I really wanted the application we're going to see later, I really wanted these cells to contain only regular elements. I thought, can I remove any of these assumptions? and I also want the converse to be true. So these are the questions that I saw this theorem, and these are the questions I wanted to answer. Can we remove the simply connected assumption? I don't want to just use this theorem when the group's not simply connected. What happens if we remove the Coxeter element assumption or the length assumption? Or both. And what about the converse? The converse true. So if this Bruhat cell contains only regular elements, does that mean that vial group element is Coxeter of minimal length? I mean, it's a converse. So let's look at an example to see what could or could not be true. Let's play with GL4 and get us to start maybe how we could change this theorem. Or to strengthen it, or to get the converse. The strengthening meaning removing the simply connected part. Can you do that? So let's look at GL4. So in this case, B tilde will be the upper triangular matrices in GL4.
Listen, we have a really dumb question, I'm sorry. Is the group actually finite or infinite?
These are infinite groups.
Oh, they are infinite.
Right,
It's
the
FQ bar,
example,
right? Is that what?
Yeah.
yeah, this is, I had bar up on the slide, I should have had it here as well. It's if you're thinking 4x4 matrices with this one example I had up here, where it's the SQ bar means the algebraic closure of this.
Okay.
So it's going to definitely be, these algebraic groups are all infinite. Infinite in number. Okay. Yeah, so when I say GL4 here, I mean 4x4 matrices where the entries are in some algebraic closure of some finite field. Okay? My shorthand. Okay? No, got it. All right, and then T naught tilde will be the diagonal matrices. This our torus in this case. The vial group is S4 in this case. And the distinguished set of generators are these transpositions. Are the ones that correspond to the three simple root subgroups. All right, what about the pre-images of, so if I take any element in the vowel group, there will be some permutation on 1 through 4. So here's an example. What would be the pre-image of this look like? You can write one of the pre-images, more than one thing that maps to this, but a pre-image would be a permutation matrix like this. So this is nice computationally, right? You could just think of the identity matrix, and to get the pre-image of this, what do? I move column 2 to column 4 of the identity matrix. So if I visualize the identity matrix here, column 2 has gone to column 4, right? Column 4 has gone to column 3, and column 3 has gone to column 2 from the identity matrix. So that's how you can see what the pre-images of these vowel group elements are in the normalized pre-image. All right, what are the Coxeter elements of minimal length? I did computed them out here for you. I multiply my permutations right to left, all right, because I think of them as functions. And in some books you pull out an article of permutations and multiply left to right. I'm multiplying them right to left. And if you do that, then if you multiply the other way, you'll just get these 4 cycles in a different order. No big deal. All right, so these are the ones of minimal length, but that's not all the 4 cycles. There's 2 more, and they're still Coxeter because by definition, Coxeter elements are this element and all conjugates of this, and all the 4 cycles are conjugate to each other. I explored that in the first abstract algebra. Conjugates of SL are determined by their cycle type. So, all right, so we're still in our GL4 example here. We're trying to investigate what could go right or wrong with Steinberg's theorem when we change assumptions. So what I'm doing here. So let's take a Coxeter element of minimal length, and this if we take any element in here, it's a 4x4 matrix, so it certainly acts on this vector, right? Just multiplication of this 4x4 matrix with that vector. And now let's make it a little more concrete. Take 6 2 matrices in our Borel group here, and let C be equal to this product. Our W again here is a Coxeter element of minimal length. Then you can check. It's not too hard to check that there is a vector in V, so that's this vector space here, and it depends on which Coxeter element you pick, such that these 4 vectors are linearly independent. If those 4 vectors are linearly independent, the minimal polynomial needs to be of degree 4. You're going to get 4 linear independent vectors, the degree of the minimal polynomial has to be 4. All right, so this only contains regular elements. And now I'm going to do an example of my example. I like to do this when I teach too. So this is an example, but let's do an example of my example, meaning I'm going to pick a particular Coxeter element here, particular A1 and A2, and show you how this happens. Okay? All right, for notational purposes, let's let EI be the column vector with a 1 and the I is plotted zeros everywhere else, pretty standard notation. Let's take W to be 1, 2, 4, 3. 1, 2, 4, 3. That's a minimal length Coxeter element. Let's take U to be any upper triangular matrix with 1s on the diagonal there. This will be like my A2 here. A1 is the identity. I'm going to take A1 to be identity and A2 to be this U. Oh, I guess it's the other way around, isn't it? Sorry. I took this one to be the identity and this one to be the U. Okay, I put it on the other side. And that product there. So C I'm taking to be U and W dot. And if you do this multiplication, C times E2 is E1, and all these you can check if you're getting bored of my talk. You can do this yourself now. Check my work. So, and those are clearly linearly independent, right? Because E2 and E1 are linearly independent. And then when you take C of E2, this is the first time E3 appears. And then when you take C times that by C, it's the first time E4 appears. So those have to be linearly, beginning with what's called a cyclic basis. All right, so those are linearly independent. This works, I mean, it's a very concrete, very specific W and very specific U there, but this pattern happens in general. When you have a Coxeter element of minimal length, you can do this and get It's set up like this.
I don't think you use minimal length.
Yeah. What happens is you don't take a cluster element in minimal length and you start doing this iteration like this, these will not be linearly independent always. And I will show you. I'm going to show you. The example continues. Let's take a Coxeter numbering element that's not a minimal length. 1, 3, 2, 4 there were 4 cycles that weren't a minimal length, and this was for one of the 2 that weren't. And now let's take a U even more specific. I had A, B, C, D, E, and F in here. Now I'm going to put 1s and -1s in there because I want to show you what goes wrong when you don't have minimal length. All right, this is an element in this Bruhat cell. And what's the characteristic polynomial is 4-dimensional because it's a 4x4 matrix. But the minimal polynomial is only of degree 3. You're not able to get that cyclic basis. If you tried to do the same setup here, you would notice that these won't be linearly independent. You won't get the. What's nice here is the E1, E3, E4 appear at the end without any coefficient in front of them. So there's no way to get any dependence relation. And you don't have that nice setup in this one. Okay, so the minimal length assumption seems to be necessary. The simply connected, maybe not, because GL4 is not simply connected. All right, so it seems like maybe we could prove Steinberg's result for GL. GL4 is not simply connected.
I've never actually tried it.
It's because to be simply connected, you first have to be semi-simple, and it's not semi-simple. Okay, so what I'm leading up to now is a proof of Steinberg's theorem for GL and an SLN, even though GL is not simply connected. And also I'm going to prove a converse of it for these 2 cases. Okay, that's what's leading. All right, but I need some machinery. And Ehlers and Gordon provided it for me. So let's let the script C be the set of all conjugacy classes of our algebraic group. The content of a Bruhat cell are those conjugacy classes that intersect non-trivially with our Bruhat cell. And those conjugacy content are the conjugacy classes that intersect non-trivially with the Bruhat cell. What Ehlers and Gorda proved in 2007, I'll have the reference at the end, is if you take an element in your Weil group and you take a distinguished generator. Now this is only proved it, or I should emphasize, this is really important. When this is up at the top, I am assuming that my algebraic group is one of these 2, okay? We're really specific here, we just got 2 algebraic groups. If you go back down to here, made me think about it, because the state of this proposition. Remember that. They only proved it for those algebraic groups. All right, now if the length, this little script L means the length. We talked about what the length of an element in the Weil group means. If the length doesn't change when you conjugate by S, S is an element, is ordered over 2, so this is conjugation. If the length doesn't change, then the content doesn't change. They have exactly the same content. They intersect the same conjugacy classes. They might intersect them in different places. They probably will, but they'll intersect the same ones. All right, or if the length goes up by 2, I mean, it looks like the length goes up by 2 here, doesn't it? But there could be some cancellation. If the length goes up by 2, then the content, when you conjugate it by that S, equals, well, it still includes all the content of your original Bruhat cell, but it also is intersecting a bunch more conjugacy classes. It's the content of this Bruhat cell. And these are actually the only 2 cases that can happen. Either you can sort of a little combinatorial, our Weil group here is Sn, right? Our Weil W here is Sn.
Why can't it go down by 2? Seems like if it can go up, it should be able to go down.
I think he can, but I'll have to get back.
Well, okay.
I think it can only go up by 2, but I'll have to play now that you, I don't know why, for sure. I'll play with it after I finish the talk, to make sure that I haven't missed something here. I'm pretty sure this is only 2 things that can happen. Okay, all right, so they proved this proposition in 2007, and now let's let WI be this n cycle. What is this n cycle? What have I done here? It's 1, 2, 3, 4, all the way up to n. Where this little hat means I've removed that. That little hat means I've taken that out, and I put it at the end. So it's still an n cycle because there's n distinct. So for example, in GL4, 1, 2, 4, 3, this is W3. I've taken 3 out and put it at the back. Okay. What's WI? So I'm just notation here. And then a W is actually a Coxeter element, a minimal length. If it's a minimal length, then it's going to look like either WI or the inverse of WI. There are certainly n cycles that aren't of this form. In fact, let's go back. Let's come back. This one's of that form. Right? I took 1 and moved it to the back, but it's thickly. All right, this one's of that form. I took 3 and moved it to the back. This one's of that form. I took 2 and moved it to the back. And this one is the inverse of that one. All right? And neither one of these are that form, or the inverse. It's got a WI or a WI inverse. So in fact, a Coxeter element is a minimal length in this group, in these algebraic groups, if it's of the form WI or WI inverse. Okay, so now here's Steinberg's theorem for these 2 groups, extended to include GLN, and I've got the converse here. So what I'm saying is, if you take a Weil group element, then this Bruhat cell contains only regular elements, if and only if W is the Coxeter element of minimal length. So we've got the converse going, and we have it true for both GLNs. Okay? So we got to do a proof, one proof. Here it is. Every talk has to have one proof, right? I hear that all the time when I go to the talk. Here it is. Sorry, this is a sketch. All right, for the backwards direction, because SLN is simply connected, that's exactly Steinberg's theorem. All right. For the GLN, what the proof is, so this is a sketch here. The proof is that you show that you have that cyclic basis, like I did for the GL4. We showed that we had the E1, CE1, C squared E1, C. You can do that if you have a Coxeter element and minimal length. You're always able to get a cyclic basis. And it really has to do with the set. It really helps that you know now that the Coxeter element with a minimal length is this form. It's basically, it's like, I don't want to. You have to use that it's a minimal. You have to use that it's of this form in order to see that you have to get this cyclic basis. All right, what about the other direction? So the other direction, I'm assuming now that my Bruhat cell, so the other direction is the converse of Steinberg's theorem. I'm assuming my Bruhat cell contains only regular elements. And I want to show that W is Coxeter of minimal length. Well, what if it's not even an n cycle? Then things really go wrong. Because if this up here, when it's not an n cycle, is just using linear algebra. Right, but I'll go through it quickly. So if W is not an n cycle, then W is a product of disjoint cycles. Let's call them n1 up to nm. So the characteristic polynomial looks like this. And notice that 1 has multiplicity greater than 1. So there is a root of multiplicity greater than 1. But if you let capital L be the least common multiple of these n1 up to nm, then the minimal polynomial will divide that polynomial which has distinct roots. So your W is diagonalizable and has roots of multiplicity greater than 1, so it's not regular. So this contains non-regular elements, namely the W. All right, so now suppose that we have something that's an n cycle, but it's not a minimal length. Well, then you're going to use the this Ehlers and Gordev proposition. Right, so now we're assuming we do have an n cycle and a minimal length, and you go, this we take W, no, W may not be a minimal length, sorry. So W star is an n cycle of minimal length. Then we can write W, we may be able to write it this way. Let's assume we can for now. And suppose the length goes up by 2. Right? Then by the proposition I stated, then the content here will be the content of this union the content of this. This has if you take an n cycle, just to do a simple one, and you multiply it by, say, one of the SI, so they all 2, 3. So this is our W star, and this is one of the S's. Then, let's see, 3 goes to 2, and 2 goes to 3. 3 is fixed, so this is not an n cycle. And you can always see, if you multiply an n cycle on the right by a transposition that's of the form I plus 1, you can get, you will get an n cycle. So this is not an n cycle, so this contains non-regular elements, so this contains non-regular elements. All right, so then what do you go from there? I made some assumptions up here. I assume that W could be written like this, where the length increased by 2. So then the argument reduces down to making sure no matter what W I pick, I can always write it, starting with a fixed W star of minimal length Coxer element. I can always write it like this, and the length is going to go up by 2, up by multiples of 2. So you can just keep redefine Ehlers and Gordev and get m numbers. All right. So now we just have to walk this way. I have to walk around a little bit. So now I want to talk about why I even wanted to answer this question. Right? I've got why do I even care whether a Bruhat cell contains only regular elements or not? I want the entire Bruhat cell to have only regular elements in it, and that's what that was always about. Why do I even care about that? Right. That's what the remaining of the talk is really about. So let's let F be a Frobenius endomorphism on our algebraic group. Frobenius endomorphism. You can just, if you're thinking of your algebraic group, the linear algebraic group, a Frobenius endomorphism, the standard one is raising every entry in your matrix to the cubed power. That's a Frobenius endomorphism. And more generally, a Frobenius endomorphism is if some power of it is that standard one. So if you compose it with itself enough times, it will be raising each entry to some power of q. Okay, that's a Frobenius endomorphism. All right, and then I'm going to let G be the fixed points of that map. So the elements that in this algebraic group that F fixes. That's called a finite group of Lie type. For the graduate students in here who've never had a finite group of Lie type defined for you, now you can say that's what a finite group of Lie type is. the fixed points of a Frobenius endomorphism. Let's assume that our Borel and our torus, and I haven't defined that, that's the unipotent radical inside the Borel. Assume they're all F stable. All right, that doesn't mean the same as F fixed, remember. So a map as an element's fixed if it isn't moved by a map, right? F of G is G. But these elements, F stable means if you take something in B and you take F of it, you stay with inside B. You maybe move to a different B in B, but you stay inside B. That's F. Okay, so assume these are F stable and take the fixed points of all of them. And these so that's why I had tildes. You might have been wondering, why were you putting tildes on everything? It's because now I'm removing the tildes when I'm taking the fixed points of these maps. And this U, T, and D are all inside G.
Is T sub O the same thing as T? T2?
Yes, that should be, I missed the O there. There should be a number. All right, let's let psi be a non-trivial linear character of U, and let E be this, because this is not important. And I'm going to construct this algebra. This is a bold-faced D, complex numbers. H. H is called the Heck algebra corresponding to the Galfond-Bruhat character. All right. Now let's let D be the set of all WT, as W ranges over the vowel group of W dot here. WT, such as W ranges over the vowel group, and T ranges over T naught. D is the set of double coset representatives of U, U, and G, and that just follows from the Bruhat decomposition. We had G is the union of W and W of D, W, B, right, that was the Bruhat decomposition, but B is UT, which is TU. Alright, so this is TWTU. Alright, but W is in the normalizer of T and G, so I only need one of those two T's. Okay? Because W is in the normalizer. So if I take, I lost my union sign here. Union and use. Too many things that look like use. There we go. That looks better. Right? So I just replaced B with UT here. Right? Any questions? Got too sloppy there and made it more complicated because it was sloppy. Okay. Okay, so this is a set of double coset representatives of U, U, and G. Let's see the notation here. Let's T sub x be E, X, E. So this is an element in our Heck algebra here, because we have E something. The X is in this EG and then E. So this is an element in the Heck algebra. And in fact, if you take all of them with a restriction over here, you're going to get a basis of your Heck algebra. This is called the standard basis of this Heck algebra. By some references on there. Of course, some people disagree that this should be the standard one, but we'll take it for the standard one. Okay, so you take these double coset representatives, you form these T sub x's, and you take just those double coset representatives such that the conjugate character is equal to the character on this set, which is the unipotent group here, intersect this means the conjugate of that unipotent group. Can you define anything here? Conjugate character? Should I define conjugate character? No? Okay. Well, this X is something in the vowel group times something in the torus. So this will be an element of a Bruhat cell. And as we run through all of U and U, all of these are still in this Bruhat cell, right? So these X's here, as we multiply on the left by anything in U, we get elements in this fixed Bruhat cell, say fixed W. Why is that? Why is that note a note that's worth noting? Well, the values of the I want to know the characters of this Heck algebra. I want to know its characters, irreducible characters, the values of its irreducible characters, and they're difficult to determine in general. But if I want to know their images on the basis elements, they're very easy, in fact, to determine if these are always regular. That's why I want all of these to be regular. So I want everything in the Bruhat cell to be regular. That's why I was looking at that question. I want to find these irreducible characters, so I want that to be easy, or at least part of it to be easy. So I want all of these to be regular, which means I want this Bruhat cell to contain all that regular. Well, why are they easy to determine on? Why is the images easy to determine on the regular when UX is regular? I could go a little faster. Okay, so this paragraph up here, there's a lot of background to completely understand it, but the point of it is that the characters of this Hecke algebra can be indexed by T theta as T is ranging over F conjugacy classes of F stable maximal tori in the algebraic group, and theta is ranging over irreducible characters of T. So really just what I want you to get out of it is we can represent all the irreducible characters of H and index them by T and theta. T is ranging over certain kinds of tori, and theta is ranging over certain characters. Okay? Let's let gamma be this induced character. I'm inducing from U up to G. This is the gap on grad character. Let's QTG. This is called the green function. It is equal to dualistic generalized character. And these are only defined on the unipotent subgroup. They're 0 off of the unipotent subgroup. And this is a theorem proved by Steinberg a long time ago, I think in the 60s, that these green functions are always 1 when B is a regular element. It's a regular appearing again. These green functions are 1 when on these unipotent elements that are regular. And when they're not regular, you have to know something about the homology of the group in order to determine them. So it can be very difficult. There's again why I wanted regular. All right, and then the characters of our Hecke algebra, what are they equal to? Here's the formula for them. This was proved by Curtis in '93. The characters, this is denoting a character of our Hecke algebra. Here's our basis element. And you sum over all things in our torus here. Torus is not, this is no nada, this is no 0 on it on purpose. Now these T's are ranging over, we have different characters here for different tori. Okay? And these coefficients here are equal to this whole mess. Right? This is not so bad. This is inner product of 2 characters. This is just sizes of some subgroups. All right? Here, this is where the green function is appearing. Right? The green function is right there. If I know this is always 1, then this is much easier to write out explicitly. This means the unipotent part you can always write in these finite groups of Lie type. You can always write every element in terms of a unipotent element, as product of the unipotent element and a semi-simple element. So this means the unipotent part of it and the semi-simple part there. So hopefully that explains at least the big picture of why I wanted to know the answer to that question about when Bruhat cells contain only regular elements. All right, so but now we've got this result for GLN that I stated earlier, proposition that I proved. Let's actually use that proposition now to compute some values of some characters of a Hecke algebra for GLN. All right, but now why have I denoting it this? This is now the finite group, all right, because I'm taking the 6 points of infinite endomorphism. This is inside the infinite GLN. And its indentations changed a little bit there. All right, so now from now on, let's assume we're in this very specific case. We've got this finite group of Lie type. All right, and let's let W be a Coxeter element of minimal length. Remember that our basis here, we only took the C sub x where it was we had the situation where the conjugate character was equal to the character on this intersection. So I want to know when I take this Coxeter element, is the conjugate character equal to the regular character on this intersection? Well, that only happens twice. That only happens for this Coxeter element and this Coxeter element. Right? Well, these x's, though, aren't just coming from Coxeter elements. They're Coxeter elements times elements in the torus. Right? So I need to go a little further and look at this Coxeter element and an element in the torus. right in between here, I've got some notation just so I wouldn't have huge matrices filling up my slide. I use diagonal matrix with this on the diagonal. I'm denoting as an n-tuple. Okay, so I wouldn't have to write big matrices. This is an n-tuple. Unfortunately, this is not an n-tuple. This is the n-tuple. This n-tuple means a diagonal matrix. This n-tuple means the permutation. Hopefully that's not confusing. From the context, hopefully you can tell which is referring to a matrix and which is referring to a permutation. Okay. So let W be this Coxter element. This is the Coxter element of minimal length. And T be equal to this. Then the conjugate character equals the character on this intersection if and only if all of these are equal except the last one doesn't have to be equal. So it's a matrix A, all the way down, all the same except for the last thing could be different. You can check as well if you take the inverse one instead. It's a similar condition except that the first one can be different on the back. This is the W's I want. So I started with W's only to be Coxter elements of minimal length because those are the only ones that I'm going to hope to have the Bruhat cells all regular. But then unfortunately all of them are thrown out except for these two. But then we get some more basis elements by throwing in T as well here. And we get that these XA and YA, XAB and YAB now can be used to construct basis elements for a Hecke algebra that will then correspond to Bruhat cells that contain only regular elements. And here A and B can be anything in FQ. The star means I'm throwing out 0, which of course I have to do because I want my matrix invertible. Right, and this is actually my last slide. This is the end result here. I actually took. This is the theorem. So then I was able to. These are just straightforward, and then these were all equal to 1 on this case. So now it just becomes more like a crowning argument. I have to check when the semi-simple part of this product is equal to the element of the torus, which is what this delta stuff is coming. This is a Kronecker delta. That means this is 0 if the determinant of T is equal to AB to the 4th. This is 1 if the determinant of T is equal to AB to the 4th and 0 otherwise, right? We all see Kronecker X. This is 1 if X is Y. 0 X. That's what I'm using. Okay. So that condition is coming from this semi-simple condition. And this epsilon condition, this just means that I didn't want to go into where this just has to do with the rank of the torus, and it comes from this right here, this inner product here will be is determined by the rank of the torus. So I can write it like that for short. So I just was able to compute the character values in these specific situations. This chi here, the one last thing that I have that's in there that's not defined, I think. The chi, there was no chi anywhere earlier. We had psi. Chi turned into psi. How did that happen? There's a psi. The psi's are characters of, these are remember these came from linear, it's a non-trivial. Non-trivial, linear character of U. So if you take U and mod out by its commutator subgroup, you can figure out what the linear characters are by looking at this group, and you'll notice that what's important is just what's on the characters of this are the same, are the same as the non-trivial linear characters of this, and what's the commutator subgroup you need? It's just A1, A2, up to AN minus 1, 0, 0. So 1's down the diagonal here, and then stuff on the off diagonal. Okay? It's just a commutator. And so and this is isomorphic to FQ to the n minus 1 copies of FQ. And in this field, the characters of this I'm calling chi. So corresponding to each side here, there's a character chi of this, which allows me to write this formula in terms of elements in the matrix as opposed to the whole matrix itself. The specific entry of the matrix, taking chi of it. Okay. So what I hope to do now is, those are the only places where the Bruhat cells contain only regular elements, but there are cases where they contain almost all regular elements. There's just like a few bad ones. And so what I want to do is now compute the rest of these characters by being able to say concretely which ones are non-regular, and so you'll have a formula like this, and then you'll have adding on to this something more complicated at the end that deals with the non-regular part. Another direction I've been looking at as well is doing this, of course, outside of GLM, and I have some results for the unitary groups as well. All right, so here's the references. This is very bad. If you just want to know, the stuff I was defining at the beginning, about algebraic groups and Borel subgroups, and all that very basic background behind what I was talking about. This is really good. These are suggestions of what I like. Very background right here. This background references. And then here are the references for that are articles that contain results related to what's going on in the talk. Here's the 2007 article I actually cited within the talk, but these also contain results that are related to what I was talking about. And there's more of them. This is the Steinberg result about the unipotent. The green functions are 1 on unipotent on regular elements. Sorry, the green function is equal to 1 on the regular elements. Any questions?
When you see name of compositor, you expect some geometry, right? Is there maybe like geometric interpretation of these things in terms of some tessellations of spaces or something?
That's not something I mean, the compositor, the compositor elements, they come from, when you're talking about the Weil group. And the Weil groups are permutation, they're subgroups of Sn, basically.
Right.
And so,
which you can interpret as
so you can definitely have the
reflection.
geometry of Sn
Yeah.
and subgroups of Sn. But that's pretty vague. To answer your question, it's not something I thought about, the geometry there. Definitely an algebraic.
Thank you. I know that we have refreshments upstairs on the 3rd floor in the